Here we have another stoichiometry problem in which we're given initial amounts of our two reactants. So we start by filling in our IRF table, starting with the chemical equation on the top. We know the two reactants, we need to deduce the two products, and then of course, and really important for this type of question, we need to make sure the equation is balanced. Once the equation is balanced, we want to fill in our initial line because we are given initial amounts. So we take the initial amounts, which are masses, and we convert them to moles. Remember, you've always got to convert any numbers you want to put into your IRF table into moles. Only moles go into the IRF table. So once we've calculated from the given masses of each reactant the moles, and of course we do that by dividing the mass by the molar mass. Once we've got those two amounts of initial moles, then we feed those into the initial line of the IRF table. Remember, stoichiometry is not considered at this time. It's simply what you have initially on the lab bench in front of you, what you have that you're going to combine together as reactants. So those initial moles go into the I line, the initial line, on your IRF table. The next thing, of course, to try to decide is which of the two reactants is going to run out first. And this will be based upon the initial moles of each reactant. The best thing to do is simply make a guess. If you can make a good guess, then you find that you have chosen the limiting reagent correctly. If you make a bad guess, then you'll find you get a negative amount of that reactant, and then you just go back and choose the other one. So if we choose aluminum in this case to be our limiting reactant, we can see that all aluminum moles will react. That requires half the number of moles of iron oxide because those react in a 2-to-1 ratio. That would give us no aluminum left and a certain amount of excess iron oxide. When we see that the excess iron oxide is a positive number, then indeed we know that the iron oxide is the excess reactant and aluminum is indeed the limiting reactant. So we chose correctly, and now we move on to continue to fill in our R line in our IRF table. That is the moles reacted. In this case, these are positive amounts because these are moles of product that we've formed. Since we start with no product, zero product, the amount of product reacted is equal to the amount of product we have finally. So we're almost finished this IRF table. We have our whole F line filled in. We just need to convert this now to mass because we're asked for the theoretical yield, and the theoretical yield is usually given in mass, in grams, units of grams. So we convert our theoretical yield of aluminum oxide into grams, and we come up with how much we would get if the reaction went perfectly. That's what we mean by the theoretical yield. So we take the moles using the molar mass, we convert to grams, and we have ideally how many grams of aluminum oxide we'd form. However, if we only formed 200 grams of aluminum oxide, we're asking what would be the percent yield. In other words, how well did the reaction perform in that particular case. So we divide the actual yield, that's our 200 grams, by the theoretical yield. What's the maximum amount of yield we could get? It's kind of like a score on a test, and we do convert it to a percentage. So converting this amount to a percentage, we end up with 85.5. In the final answer, we have 3 significant figures because 3 significant figures are included in the information at the beginning.